Okay, welcome everybody, and finally we're on. So I'm going to talk a little bit about finality today. The subject is final. Final means final, and it's a deep dive into field immutability in Java. Well, admittedly, this topic is a little bit dry, so I'm going to try to spice this up with some jokes. So I apologize in advance for that. And I'm going to show myself the way out after the presentation. So I hope that's good. My name is Per. I work in the core library team at Oracle. And yes, you might wonder, isn't final final? Well, it turns out maybe not much so. So in this presentation, we're going to meet two small guys, which I'm going to present here. It's, little happy and little sad, and they will appear in different spaces in this presentation. So the road to immutability is paved with maybe good intentions, no, memes. So you're going to see a lot of those in this presentation. We're going to talk about mutability versus immutability, the tension between those two concepts. Are final fields final enough for what we expect from them? What is VM trust? And what is a strictly final field? That kind of implies that that exists a final field that isn't really strictly final. And at the end, we're going to talk about lazy final constants, which is a new concept, which preview in 25 and will now have the second preview in 26. Okay, so let's talk about mutability versus immutability. So this is my personal copy of effective Java, and item 17 says that minimize immutability, and there are many good reasons for that. So we can learn that immutability makes our program more predictable. That an immutable object can only be in one state. Immutable data can be shared safely across threads. And immutable data can be reused and cached because you can't mutate it. So you can reuse it and provide it all and over again in different scenarios. And it's also one important thing here. They can be used as keys in a map. And hence you can derive that mutable stuff can't be used as a key in a map. Is there someone else except me that made a mistake and put in a mutable key in map? Well, nice, I wasn't alone. So that's great. Functional programming relies heavy on immutability. So some of them doesn't even allow mutation, like Haskell mode. Others have this kind of escape hatch, but it's not really a model. And where you have a place in a model of the language. And in Java, everything is mutable by default. I think this was, in hindsight, a mistake. But of course, it might be the right choice at the time Java was created, but I don't think it's the right choice to this day. But here we are. And that was the heritage from C struct, of course. So immutability is an opt-in where it should be the other way around. So we can have final, we can have record, and more recently value classes, which Remy talked about perhaps 2 days ago here. It is an interesting concept, which we will take a little closer look at later on in the presentation. Okay, so let's see, how do we work with mutable objects? So in this presentation, we're going to talk a lot about a point, which is a very simple data structure. So we have a class point, which has a coordinate x and y, and we can set them in a constructor. Nothing strange there. And then we can build on point and say that we have a line that has a begin and an end. So the beginning point is, for example, in the origin, and the end point might be in coordinate 1.1, and there we have a line between those points. And that looks good. So we can create a new point, 0, 0, and we have another point at 5, 5, and then we create a line which starts in the middle and then goes to 5, 5. That looks good at first glance, but now we have a problem. Because if we provide this line to a method, and maybe we want to enforce some invariant that perhaps This line can only be in the first quadrant, for example. We need to check that when we enter the method. And if we have this kind of mutability, we open up for something called time of check, time of use race condition. And this is a standard error. We've seen this in a lot of places in the JDK in the past, and even more in user code. So we can even, modify one of the points. So we need to do something called defensive copies. So we need to create a mirror of this that is kind of detached from the original one. And therefore we have this, sad guy at the bottom. We need to create defensive copies. Imagine if we have an array, for example, we need to create an extra array from that. And that might be expensive in many cases. But remember, no matter how bad things, it can even get worse. So we can see what's happening across threads. So suppose we create a new point in thread 1 here. And then we observe that value in a second thread. And then, of course, if we try to read P all the time, it can be null. That's natural because then it hasn't been produced yet. And of course, it can be the expected way that we see 1, 2. That's quite unsurprisingly if we do that. But we can also see that y hasn't been initialized yet. So we only see x equals 1, but y equals 0. Okay, I think we can understand that because we kind of got into exactly that time when the constructor hasn't really completed yet. And it can also be the case that neither of them are set. Well, maybe we can buy that as well because now we just created the object with nothing was initialized. But we can actually observe that y is initialized, but not x. And that seems strange. But the reason for this is that the Java compiler and actually the hardware is allowed to swap places in order to try to optimize code. So if we are within the thread, all those permutations are okay because they cannot be observed by the thread who is running. And that gives us a lot of performance, actually, because we can shuffle around stores and reads any way we want in a more optimal way that it's expressed in the textual kind of way we write our code. But it's a problem when we access from another thread, because then we don't have that guarantee. So you might want to say that why do we have this? Couldn't we, for every step, make sure that a thread can really see what's there? And we can do that if we declare the value volatile. But that is very expensive. That will make our program maybe 3, 4, 5 times slower. So that's a bad trade-off. So lack of memory barriers lead to out-of-thin air values. And this is a bug that's very hard to detect. Maybe you will run this 1 million times and it seems to work, but suddenly it doesn't. So this is a very nasty bug. So final field comes to the rescue. In Java, we can unlock the benefits of immutability with final fields. We all know that. So final fields comes with restrictions. So we must assign the value in the constructor or in the static initializer if it's a static field. And they cannot be assigned afterwards. And by cannot, I mean it's not impossible to do it, but it's not easy to do it. We'll talk about that more in a few minutes. And it implicitly adds something called a memory barrier after the constructor that allows this to have safe publication. Safe publication means that you construct an immutable object and then you can share it to another thread. So the details will come in the next slide. And a class whose fields are all final can be an immutable class. It doesn't mean it has to be, but it can be an immutable class. And an immutable class, if we create an instance of that, it's called an immutable object. So if we deep dive a little bit into immutability, there are some surprises there. So for example, an immutable class can have one or more mutable fields, but still be immutable. That sounds like a contradiction in terms. But for example, a string has a hash field that is mutable. It's kind of caching the hash code, so we only need to hopefully call that computation once. But the thing is that this field is encapsulated. It cannot be observed from the outside. It's a part of the internal of string. So therefore, it's still immutable, but internally it's mutable. We can also look at it the other way around. Suppose we have a class where all fields are immutable, but then we can the class itself is not final. Then we can subclass it and introduce immutable field that can be observed from outside. So it's not really strictly immutable in that sense. And you know, it's more complicated than that. So we might have a final field which holds mutable data, but if we have a reference to that mutable thing that's final, we can mutate it underneath. So that means that this object is only shallowly mutable, which is a term that's been used quite frequently. So it's very complicated. We can try to come up with a definition. No sequence of operations can be invoked by a set of threads to enable an observation of a change of the object's internal state. But it turns out this is almost right, but not completely right. So it's very complicated. Okay, so let's go about and make our point class mutable. So we declared final because we don't want anyone to override it. If we want, we can also make it sealed so that all implementation of it, we will have control of that. But final is this kind of sledgehammer that you said. This is the only one. With sealed, you can say that, well, there is a enumerated number of subclasses, and then we can take control of all of them to ensure immutability. And then we do the same with line. And then we create a point, we create a line, and then if we try to mutate x here, for example, we can't do that. So that's great. And that means that we can compose them without defensive copies. And that's a big win. And it's get better. So if we try to share this across threads, we create this object here. And if we go to the details in the Java language memory model here, we see that the semantics of final means that we have an implicit memory barrier inserted after the constructor. And what is a memory barrier? Well, a barrier in a memory means that we impose restrictions on reordering. So in this particular case, it's a store barrier. It means that stores before the barrier cannot be reordered with stores after the barrier. And of course, the pointer itself is assigned to P after the constructor is run. So that means if we can observe P, we know that all the actions happens before we see P. Happens before is another term here that you can read quite a lot of in the Java memory model. So that means that the changes to X and Y happens before we can actually observe P itself. So that guarantees that we see only two cases. Maybe P is not initialized yet, and then we see null, or we see the correct values. We can only see Px1 and P.y equals 2. That's the only combination we can see. And that's great. That's what we want to see. So no out of thin air values anymore. Okay, here is an example of how we can reuse objects and share them. I guess if you have a geometric application or a game or something like that, it's kind of one of the most likely points you will create is the origin, that is 0, 0. So we can provide a static method that provides that value that's been created once and for all. Okay. So are final fields final enough? And what do we mean by that? Well, final fields indeed can make our programs more predictable. We already spoke about all these terms here. And in addition, we can make our application more efficient because fields cannot be updated after they have been initialized. So in theory, the VM can, if it observes one value, it knows that this can never change. So maybe I can, inline or constant fold this value, and I don't have to even look at the value anymore. So the question is, are final fields enough to unlock such powerful optimizations? So let's see. Here is the class we just had a look at. It's the final class point with final fields. We create that object. And we do some reflection here. And we say that now I want this field to be updated. If the reflection. And it turns out now I can set this. And this, ruins everything. That means we have a backdoor to update this value. And therefore, the VM cannot really trust that this value is never changed. So final fields can be updated with reflective rights. And what do you think is the reason for this? Any suggestion? What's the worst mistake we made in Java? Yeah, exactly. So that is the problem. So we have we can take a look at this picture. Here it is, black and white. So that's the reason. So before, that's the next slide. Sorry. So before Java 5, we couldn't actually modify final fields. But there were so many libraries that relied on serialization. So we had to provide some kind of thing that bypassed this kind of stuff. So that was kind of a tension between finality and the ability to serialize the stuff. So we made a mistake there in hindsight. Yeah, this wasn't good. So we are paying the price. It comes back and bites us now, even 20 years later. So we are trying to fix this. I mean, Victor had a presentation here last year and even this year talking about marshalling, which will be eventually something that supersedes serializable. So that's good, but until then, we have other means to try to mitigate this problem. So let's see what happens here. We have this class, we have this reused object called origin, and then we want to perform some arithmetic on this. We want to take origin x plus origin y for this, origin. So this, in theory, should be 0 plus 0, which should be, of course, 0. But if we look at the code that's been generated using the hotspot compiler, we see that, unfortunately, this is not the case. So the long address you see up there, that corresponds to the constant origin up there. And then we take a look at some field that offsets 16, and then 4 bytes more. We add that value, and that's the result. So this shows that we actually have to compute this value. It cannot be constant folded. So that's very unfortunate. I mean, just for this computation, it might be okay, but we don't have this nice transitive property that can constant fold in several steps that we'll take a look at in a few slides again. But what happens if we make this as a record instead? This is kind of equivalent to the class we had before. Record point, int x, int y. And then we have this static field of origin there. And what happens now is that this will be constant folded. This is 0, and you might think, what's this XOR? It should be something like load 0 or something. But this is a kind of a compiler trick that it turns out that if you XOR a value with itself, it's always 0. So this is kind of a trick. So this means set EIX to 0. So that means that we can constant fold if you use the record, but if you use a class with all final field, it's not getting constant folded. So this kind of pushes us to use records more. We get more performance. So that's great. Access to record components can be constant folded. So let's look at a more contrived example. Let's say that we have a list of 1,000 points. And we have some method that returns a list of all the points that are within some kind of circle that's defined by a point. So we have this circle, and we can see if the point is on the origin, it does not completely enclose a point. So therefore, we know that the list is empty. But if it's not the origin, we're going to iterate over each and every point, and I'm going to apply some filter, which I'm not going to show here, but it will use some kind of arithmetics there. And then we will convert it to a list. And then we invoke it with the origin, of course, because that's what we are interested in. So there should be a lot of potential for optimization here. OK, so let's see. We know that the origin has a point x and a point y, and we check if they are 0 because the parameters there are 0 and 0. And we know that point x and point y is a constant, so we know that this expression is true because we can constant fold it. Now we know that the branch will always take the first branch, which is return list of. So we can replace everything with list of because we can constant fold. And now we see that it's not, we don't have to even invoke this method here because we will always have list of, so we can inline that. So now list point of the wi is list of, but it turns out list of itself is just a method that points to a constant, points to immutable collects an empty list, which is a constant. So even if we use this wi in a larger kind of context, we can continue and constant fold. So this will give us a lot of performance. So stay strong, constant fold. Okay, this leads us to trust. Why was the record trusted, whereas our custom class was not trusted? What's the magic here? So let's see and kind of disclose why this is the case. So for the hotspot, this is determined by a class called CI field.cpp. And if we look into the details, this is very deep into the VM. We have a method called trust final non-static field. So this kind of shows us that a static field is always trusted. But if it's an instance field, it might be trusted if this method returns true. So we have some internal packages that they get special treatment, because if they didn't, the JDK would be slow. So some of them, notably in Java Lang, are all trusted by default. And there are some other internal packages here which are trusted by the VM. Then, more interestingly, we take a look at what other cases are trusted in this way. We can see that if the class is hidden, it's trusted. Why is that? Yeah, because if it's hidden, we can't use reflection on it. We can't use unsafe to get offsets. We can't use set accessible, things like that. If it's a box class, then it's trusted, like integer long with big letter in the beginning. If it's a record, that's what we were just doing the trick. It's trusted. And, well, I think this one, Java Lang string, is kind of a redundant thing because we already trusted everything that is in Java Lang. So this is I think this is redundant. But if neither of all these checks succeed, we return a parameter called trust final non-static fields. And this is kind of an escape hatch that you can use. So constant folding trust all static fields. Constant folding only trusts a subset of instance final fields. And we can use this escape hatch called trust final non-static fields. So if you have a Java application, you know you're not using serialization, you can provide this switch here and gain some performance. So I think that's a thing you should bring home and test. Because now it will trust all classes. Okay. In theory, I think the VM could speculate whether or not a field was updated. Maybe it can generate an uncommon trap if we update it. But this is all very complicated, so we have another idea to do that. So let's look at that instead. We are looking at something called prepare to make final mean final. That means that finally final will be final, which was in the title of the talk. So we're going to, over time, introduce kind of a switch that can control the interpretation of finality. So you must grant on the command line for a module name to enable final field mutation. And if it's not declared there, it will be deemed illegal. And from the beginning, it will generate warnings, but as times pass by, if we are progressing to higher and higher JDK, it will be more and more restrictive. Warnings will become errors, and the more lenient policy will be removed. And this is a part of the integrity by default push that we started quite some time ago. And this is very similar to unsafe, JNI and FFM and dynamic agents, where we can now allow them in the beginning, but give the developers time to migrate. And there is also this, enable field mutation stuff they can use while you are, improving your code. Great. So here's what's going to happen if we have this class, and if we have this final means final, we will get a warning. And in some releases, we will get an error unless we have this switch for that module. And eventually, we can never use it. So that's good. We have control over the situation. And maybe then if we allow it for some module, constant folding can't be done there. But if we disallow it in all the other modules, we can constant fold that. So there we get kind of the best of two worlds. Okay, so our final fields to final. Let's see. Okay, there's a thing before that. So are there actually final the final fields? Well, they are final, but there is a glitch. You can actually observe a value during construction. So that is a problem, and which we are working on to fix. So it's kind of a, let's see, complicated thing. We need to keep track if an instance is in the construction. So we don't want to do that. So we want to have a more principled solution to that. So we want to be able to guarantee that it's can only be observed in one state. So let's look at early reads. So this is a kind of modification of our point class. Or we have a method called leak y. So we start with this point, we set x, then we leak y, and then we set y. And of course, the leaky y will print 0. So that's not good, because it's not designed yet. So that means that even though it was final, we can see another value that's being initialized. So that's not good. Okay, so we have something called strict field initialization in the JVM, which is a preview feature. And this is something we needed to do for Valhalla for the value classes. So this is kind of a spin-off for that. So it provides safe initialization of value instances and a safe initialization of null restricted fields. So we can never observe that if a value can never be null, we can never observe null. So that means that they are strict final fields, meaning it's kind of a more guarantee than final fields. So they must be initialized before the call to super. So therefore, we need another JEP called flexible constructors in order to do that. Before, super was always called implicitly or explicitly at the first statement. So they cannot be reassigned after super call. So that means strict final field can only be observed in one state. So we can either write before super or read after super, but never both. So that gives us an even more strict view of final fields. So this is on the left-hand side. You see the old kind of way of doing things. We create the object. Here in this example, we have C, which extends B, which extends A, which extends object. And we initialize the object. We initialize the uppermost class A, continue to B, and then to C. That was the old way. But in the new way, we have this kind of early larval and late larval state. So we have early inlet of C, which can only write C's fields. And then we can write B's fields and write A's fields. Then we invoke the topmost object. And then we can do late initialization, which is reading, but not writing. So this gives us a strict field. So now if we are trying to leak this value here, we can see that now the fields are strict here. If it's a value class, at the left-hand side at the top, you see we have a value class there. And then the leaky Y is an error, because we can't access this before a constructor is called. So I think that is a step forward. And you can actually do this today. They are not called strict fields, but you can move your constructor in different places to prepare for this. Strict final fields can only be read after they have been initialized. Wow, that's great. Okay, so that also means that strict fields can be trusted. So if we have a value class of point X, you can't use a value class yet. You have to wait for Valhalla. But this is how it's going to look. So you have a value class of point X, and then it can be constant folded. So this is another trusted entity. Strict final fields can be constant folded. Okay. Now we're coming to lazy final constants. So we have, on one hand, final fields and we have mutable fields, but are final fields too final? Are they imposing restrictions, the semantics of final fields that we don't like? So a class can, for example, have many fields, and that makes us want to shift field initialization for later. Or it might have field initialization that might be expensive. Maybe we are, invoking some web service, reading something over the internet, or reading a file or something like that. And maybe just a small subset of these fields are actually being used. So we want to do things lazily, but we don't want to pay the performance price. So this is kind of up until now, final is kind of inflexible. So they must be initialized by the end of the constructor or static initializer, and it's impossible to move initialization of final field around. And you can't initialize it with another thread, for example. It must be the same thread that creates the object. So the question is, are final fields too final? Well, that depends. Let's see if we can do some lazy initialization. So in this example, we have an index, and then we have a list of strings with coordinates. I mean, the strings can be like 10, 20, 40, 50, and things like that. And the idea here is that we want to parse those string values. And parsing string values is relatively slow. So we do this eagerly. We provide this list, and we can parse them directly and put them in here. That will work. But it's slow, because we need to parse them regardless if we're going to use them or not. If maybe we're just interested in X. So let's try to make this lazy. We can convert the fields to mutable fields and set them to some sentient value, indicating that they haven't been set. We carve out the sublist from this index, and if we call X, we check, is it this sentinel value? Yes, okay, that means that we haven't initialized it yet. Then we initialize it and set it. Otherwise, we just return X. And this opens up a can of worms. It's not a good thing, because coordinates are passed lazily. Oh, that's good, of course, but the bad thing is that we need to give up immutability. That's not good, but because we want immutability, We have sentient values that are used to mark initialized coordinates. So maybe we want to actually use the value -1. If we do that, we have to call and parse it all over and over again. So that's a problem. And concurrent access can result in redundant initialization. Maybe we call X from several threads. And if you have listened to all the other problems we have, you will realize that there are a lot of crybabies left there in terms of visibility and other stuff. So this is really, I would call it a disaster. So that was not a good attempt. So lazy initialization and final field don't go well together. For static fields, you can use something called a class holder. You can have a class where we have a value, and that works pretty good. But it adds to footprint. But for instance field, there is actually not a good way up until yet. You can fall back to mutable fields, but then you have no constant folding. We still have to use synchronization and so on. So this has been a problem from day one for Java. So can we do better? And of course, I wouldn't ask that question if we couldn't. So there is a hidden gem in Java called stable, @stable. This is an annotation. And it asserts that the field can only change once from its default value. So when the VM sees a field that is not its default value, that's for reference, it's null, or for an int, it's 0. So for an integer, if it sees 5, for example, it knows that this value has been updated, and now I can constant fold it. So that is the magic sauce. Now, unfortunately, you cannot break this promise, because if you break this promise, the VM might have inlined this value 5, and you update it to some other value, let's say 8, and then your program is completely inconsistent. So this is inherently unsafe. And that is the reason why it only can be used in internal JDK code. You cannot use this in your own code and gain something. You can do it, you can annotate it, but it doesn't mean anything. So a stable field is a plain mutable field annotated with stable. And at first update, the VM treats it as a constant. And it actually works on arrays too. So if you have an array that's stable, it also trusts all the components in the array as stable. But it doesn't work on linear memory, such as memory segments, or as I said, your own classes. Non-JDK classes will not be affected. And we use stable a lot internally in the JDK to perform performance and lazy computation. For example, in method handles. But it's, as I said, unsafe. So multiple threads can race to set the same stable field. Different values can get constant folded in different parts of your application. And update to 0 or default values are ignored. So if you actually want the value 0, it's not getting constant folded. So if it only was a way to bring stable to third-party libraries and your developers, and we are kind of in this situation. We want both, but now we have JEP 526 that comes to the rescue. So what is this? A LazyConstant is a safe wrapper around stable. It's an API-based approach like thread local, scope value, and class value. And it guarantees atomic, at most once, mutation. So a LazyConstant is created using an underlying computing function. That is a lambda that tells how to compute the value. So we know how to do it. It's the recipe, but we won't compute it now. So on the first access, we will invoke this underlying function, compute the value, and initialize the LazyConstant. And if it's initialized, the VM can optimize it with constant folding. So that is actually what we want. So when we have this now laziness versus deferred immutability, we now can pick both. So that's great. Pick them both. Okay, so how does it look like when we are using LazyConstant? So now we can say that we have a final LazyConstant, and this assumes final means final. I want to say that I don't use a record here, but you could use a record if you want to use it already now. We have two LazyConstant of type integer, and here is the recipe for making them, and then we just invoke a get for x and y, and this will work even if we have this, sentinel value like 0 or anything like that. So I think this is much nicer. And the best thing with it is that it actually works. It doesn't have any of the drawbacks. There are no crybabies here. So great. No more mutable fields. Safe and atomic updates without any sentinel values. And simpler access. Initialization logic is provided at construction. So you can see also here, when you define your value, you see when you create your LazyConstant, you can also see how it's supposed to work. So they are kind of tied together. Okay. Often LazyConstant comes in groups, so there is also a collection around this, so they can share the same initialization logic. Okay, so that means that we don't need a lambda for every LazyConstant that is in a group. So the solution is to use LazyConstant, and this is a part of JEP 526, which provides an unmodifiable, that means shadowly immutable collection whose elements are created lazily. And once they're computed, the elements are stored in a LazyConstant itself under the hood for later use. And again, we can use this LazyConstant API for that. So we can have, for example, a list of points. If we have a polygon with points, this is now not a line, but a polygon which has several points. And you can provide a list of strings. Remember all the strings that we would like to parse afterwards. So we have a list of lazy, which is a new factory that's tied to a list. We have this size, and then on the next line is a recipe. We have an index for which we want to compute a value, and there's the lambda. We create a point. And remember, point now is also lazy. That's the old lazy point from the previous slide. So we have two layers of laziness here. And then if we want to get something at the index, we just get that. So that will, when we go there the first time for an index, it will invoke this lambda, which will create a point. But we haven't parsed yet. The point is just a holder around that. Excuse me. So the coordinates are parsed lazily when the accessor is called. And the lazy list use one lambda expression for all elements. Remember, it's not free to create the lambda, but here we can amortize the cost of the lambda over several elements, maybe hundreds of them. Excuse me. Okay. Mutable layers of laziness list elements are themselves lazy. So let's see how this works in reality. So up there we have the polygon, and at the bottom we have the list of our strings. And remember, you can see on the left-hand side how the list looks like with all the strings. So the first one is rect get 1 x plus rect get 2 y. So when we invoke get 1, we will create the first point, which is turn is lazy. And then we come to .x. That will actually do the actual parsing because point is lazy. So it will only parse the x component. Then we come to rect get 2, which will create this lazy other point. And then we invoke .y, which will materialize this parse 20 from the string array, from the string list. So everything here is lazy. But we only need them to evaluate what we actually need to fulfill the argument. And if we look at this, we have 10 plus 20. Those are the kind of objects we pick from the list of strings. And now we see we can actually constant fold this. this works all the way around the layers of constantness and laziness. So here we can say we have a constant 30 that we move into EIX in this case. So that's great. We still have constantness, finality, and constant folding at the same time. So summing up, I think we can look at the different properties of guarantees on the y-axis there, where we have mutable fields in the origin, which has no guarantees. As you have seen, there's a lot of problems with mutable fields. And the x-axis is restrictions. So final field comes with restriction. We must initialize it in the constructor or the static initializer. And it gives some guarantees. And then we have final field. When we have final means final, gives better guarantees, but it imposes slightly more restrictions because we can only read before we call super, and we can only write before we call super, and then after we can only read. So there is more restriction. And final means final is still final field, but I talked about strict final field, which is at the top there. Okay, final fields have more restriction because they can't be mutated by reflection. And then we have lazy constants, which has less restrictions, but provide almost the same guarantees as a strict final field. So if we try to kind of partition this, we have predictability, which is everything except mutable fields. And then we have optimization, which almost cover final fields, but we have strict fields and lazy constants. And then we have laziness, which is here, which kind of puts lazy constants in a good spot. But should we always use lazy constants? Definitely not. I think we had the overhead of creating the lambda. It's perhaps more complex than just initializing a final field. So I think you should only consider lazy constant if you have something that's expensive or is unlikely to happen. Then only then it makes sense to use lazy constant. But it's a nice part of the toolbox. Okay, summing up, final field brings the benefit of immutability to Java. Immutable objects can be composed without defensive copies. Immutable objects can be safely shared across threads with no synchronization. But final fields are not enough to unlock powerful optimization. Final fields can be updated with deep reflection. That will be fixed with final means final. Final fields can leak before initialization. That will be fixed with strict final fields. And final fields are also too final to support lazy initialization. And for that, we have lazy constants. So, how final should your final fields be? Well, it's up to you. Now we have the toolbox, and I think you have a better understanding of how final fields and mutable fields work. So regardless of what you want, we got you covered. Okay, don't forget to sign up for Java 1. And with that, finally, this finally means final presentation is final. So thank you. And I'll be happy to take questions either now or you can come to me here and talk to me. Yes, question there? Okay, so I think the question is what will happen with different threads if you have a lazy constant. Is that correct? And the thing is that lazy constant guarantees that only one of the threads will win. So the other threads, they will be waiting and they will see the new value. So it's guaranteed that they will not. It's the invoke at most once guarantee on that. They are blocking, yes. That's true. Hey, yes, question?
Hi. Can I opt out of laziness?
Can I opt out? Yeah, you don't. If you don't use lazy constant, you opt out.
I want my server applications to start up and pay all of the taxes up front.
Yeah.
And not while I'm processing requests.
Okay, so I think you're talking about another thing. Have you did you take a look at Laden stuff? which means that you have a test run and you can save a lot of stuff that you can use for startup. Yeah. So you should take a look at Project Layden, which provides you the capability of running a test run, saving a lot of VM's data like profiling data or class information. And then you can save that into an AUT cache, which you can then provide to your VM at startup. And your program will start much faster and will warm up much faster.
But like in general, can I just opt out of the laziness and make it just be immediate?
In what sense?
Like, say I want to run my unit tests and make sure that everything actually works by making it all happen up front. Or I want to...
Every time you restart your tests, the LazyConstant will not be initialized. So it will be run every time you start a VM. Okay, we can talk about if you come to me later. Maybe I didn't understand the question. Okay, see you here at the front if you have more questions, and thank you.